Right, good morning everybody. Welcome back to the second lecture in the series. Note I've corrected the link to the additional material on this first slide. So as with the first lecture, you can access all of the slides online, and by pressing S, you'll find the speaker notes. So you can follow along with what's going on. So in the first part, I want to quickly recap and expand on some of the parts that we did yesterday. So in the first lecture, I was looking to emphasize the modeling, approximations, and limitations of what goes into one of our numerical simulations. And most of these approximations and limitations come from a mixture of physical and resource, usually computer resource, limitations. So that's leading us to consider the most important features of our models, what aspects we need to model, and in what order. So the key points I wanted you to take away from the first lecture were that conservation and balance laws are generic features in matter simulations, that these will themselves generically lead to shocks, that these shocks appear in mergers, and that they are crucial to the development of the numerical methods. Now, as this appears in pretty generic matter simulations, we can beg, borrow, and steal techniques from the Newtonian computational fluid dynamics community, but we need to specifically and carefully consider issues that are linked to general relativity and to neutron stars in particular, such as the increased cost and practical complexity and the additional physics issues that come about from, for example, the surface-atmosphere interaction. So today's lecture is going to head reasonably deeply into the numerical methods. We'll look at some of the standard techniques used in the field. And this is really where I would strongly encourage you to look closely at the exercises associated with these lectures. They tend to focus on one and only in a couple of cases two-dimensional algorithms, but they highlight the difficulties, the limitations, the costs, and particularly the complexities, because there's no good unique answer as to what's the best numerical algorithm for dealing with neutron star simulations. It's got to be a balance between an algorithm that's sufficiently complex that it gives you results accurate enough for the physical purposes you're interested in, but not so complex that you would struggle to implement or maintain it yourself. And that balance is very definitely an individual thing. So to highlight or summarize the discussion of the equations of motion, the full form of balance laws that we would typically try and evolve are pretty much as framed here. In fact, this is going rather far beyond what we looked at in the first lecture. So we've got our standard balance law terms, so the time derivative of whatever our quantities are that we're evolving, but it's usually linked to energy and momentum, is balanced off by the gradient of the fluxes. But there may be additional pieces that can't be written in conservation or balance law form. So we'd have a matrix A contracted in with the gradient of the quantities themselves. On the right-hand side, we'd have the terms that we would think of as generating or exchanging energy and momentum between either the fluid itself on the micro scale or other parts of the problem. So the first piece is a diffusive term with a D diffusion matrix and a second derivative piece. And then we've got an algebraic source term S. Now, in the full general case, the matrices, the A and D matrices, are going to depend on the data itself. And things like the source terms or even some of the matrices may even depend on non-local operators. So an example of this would be radiation transport, where the exchange of energy momentum between the fluid part and the neutrinos or other radiation parts might depend on an optical depth, which is computed by an integral over space-time. However, this full framework that I've written down is far too complicated for both practical implementation, but also the particular situations that we're interested in. So for the bulk of the space-time, for the majority of the situations that we're interested in, the Reynolds number is sufficiently high and the motion sufficiently fast that we can completely ignore the diffusive term on the right-hand side. So we just drop that piece completely. If we're just dealing with single fluid hydrodynamics or single fluid magnetohydrodynamics, then we can write everything in conservation law form. So we can drop the A term as well. And finally, if we're not dealing with radiation transport, or if we're only looking at the simpler models of radiation transport, then all of the terms, the fluxes and the sources, can be assumed to depend on local operators. So we're left with the time derivative, the divergence of the fluxes, and the source terms, and they're all going to be algebraic operations of the conserved variables, usually the energy and momentum, and other constitutive variables, Q. Right, so from a mathematical and implementation point of view, it's the principal part that matters. It's the part with the highest derivatives. And once we've thrown away the diffusive terms, that means that we're going to focus on the divergence of the flux, the div f term. Adding in the source term is algorithmically relatively straightforward, provided that source term doesn't vary on too rapid timescales. And I'm not going to touch on that today, but I will talk about that at some length tomorrow. So for now, we're going to focus on the conservation law form and the numerical methods that we need for that. So in the conservation law form, we've just got time derivative of Q plus divergence of F equals 0. Right, one more recap and extension of what we looked at yesterday. So we talked about the characteristics and characteristic speeds. So for a scalar conservation law, so dtq plus dxf equals 0, we can, as long as the solution is continuous, expand this out as dtq plus dqf dxq equals 0. So this looks like an advection equation locally, where the information is propagated to the right with the characteristic speed dq of f. Now, we want to expand this or extend this away from the nonlinear scalar case towards systems. And it's easiest to consider the linear problem first. So for a linear system, we have that the flux is given by some general matrix A multiplied by Q, where the matrix A here has constant coefficients. They don't depend on the data. So that means that we can expand out, we can pull the matrix through the derivative, and we end up with dtq plus A dxq equals 0. Now, at this point, we have to appeal to a crucial aspect of the conservation laws that we're dealing with. We have to assume that they are hyperbolic. For our purposes, what that means is that the matrix is diagonalizable with real eigenvectors and with a complete set of real eigenvalues with a complete set of eigenvectors that totally span the vector space given by Q. What that means is that on diagonalizing the matrix A, we can do a conversion to the characteristic variables W. So W here are given by multiplying the matrix of left eigenvectors into the original variables Q. What this means is that the evolution equations for the characteristic variables are given by dtw plus lambda dxw equals 0, where lambda is a diagonal matrix. That means that the evolution equations for each individual component of the characteristic variables decouples from all of the others. We can treat each one as its own separate advection equation. Now, because we've done this by diagonalization, the entries of the lambda matrix are the eigenvalues of the original Jacobian matrix A. So that means that the information contained in the characteristics is being propagated around with speed coming from the eigenvalues of this Jacobian matrix. We can therefore use our solution to the advection equation, so trace the solution along the characteristics, because it's going to be absolutely, the solution is constant along each characteristic separately, to find each component of the characteristic variables W. At some future time, we will therefore know all of the components of the characteristic variables. They'll have come from different points in the initial data slice because each of the characteristic speeds will be different. We can then convert back from characteristic variables to the original variables by multiplying by the matrix of right eigenvectors. Now, in principle, we might think that we could extend this to nonlinear systems, because we could expand out a general nonlinear conservation law in the same way. We'd have dtq plus dq of f times dxq equals 0, where now dq of f is the Jacobian matrix, so it's the derivative of a vector with respect to a vector. And we would then locally be able to treat this Jacobian matrix, which does depend on the data, in the same way as we've done here, by calculating the characteristic speeds through the eigenvalues and calculating the eigenvectors to convert to characteristic variables. And this certainly has some advantages, and we will see that appearing in some numerical methods. However, the problem is that when you use these nonlinear characteristic variables and characteristic trace forward in time, when you try and convert back to the original variables, you need to use the right eigenvectors, which themselves depend on the data, but you don't know the values of the data because you only have the characteristic variables themselves. So in general, this approach is somewhat impractical and we have to use an alternative approach. But the viewpoint of using characteristics is fundamental to a lot of numerical algorithms. So Mukesh has asked, is it always possible to diagonalize the matrix A for the advection equation? And the answer is that if your conservation laws are strictly hyperbolic, then it is always possible to diagonalize this matrix. For general matter models, it is always something that you have to check to see that the system is genuinely hyperbolic in an appropriate sense so that you can calculate this information. It's certainly the case that for the equations of hydrodynamics and the equations of magnetohydrodynamics, that all this information can be explicitly calculated. It's not so clear that it's necessarily true for all extended matter models. In particular, it seems to be the case that if you look at multiple interacting fluids, it's possible that there's regions of parameter space where it's not hyperbolic in this sense. Okay, so moving forward, we want to use the characteristic viewpoint to discuss the basic wave types, because they're each going to have a role to play in what comes. So the picture here is starting from very simple initial data. What it's doing is it's solving the shock tube problem, sometimes also called the Riemann problem, depending on context. So the initial data is piecewise constant. So the initial discontinuity is at 0.5. Initially, the data to the left is constant. And if you look far to the left of the picture, you'll see what the value is for the pressure, the density, and the velocity. And also to the right of the discontinuity, the initial discontinuity, the initial data was also constant, with essentially the same zero velocity but a lower density and pressure than on the right-hand side, than on the left-hand side. So there are characteristic waves associated with each eigenvalue of the Jacobian matrix. So when working with fluid equations, the Euler equations, in one spatial dimension, we have three equations of motion, so three characteristic waves. And here we can see the most common three types of behavior, and each of them can be explained via the characteristic information. So the leftmost wave, which is roughly in the center here, is a smooth, well, continuous wave. And this has occurred because the characteristic speed to the left of the wave is faster than the characteristic speed to the right. And by faster, I mean more negative. This means the characteristics are separating. The material is moving to the left faster on the left than it is to the right. So this wave is non-linear. It's associated with the acoustic speed, the V minus CS term, and it is continuous. So the data is spreading out. In hydrodynamics, this is referred to as a rarefaction wave. The material is rarefied as it expands. The second type of behavior is on the right of the picture. And this is what happens when the characteristics focus. Now, we saw this yesterday when we were discussing Berger's equation, when we saw the characteristics focusing in from smooth initial data, and they then broke and formed a shock. This is a shock propagating based on discontinuous initial data, but it is occurring because the characteristics are focusing. That is, the characteristics to the left of the wave are propagating faster than the characteristics to the right. This is typically associated with a jump in every single variable. So in the hydro case, we can see jumps in velocity, density, and pressure. We would also typically see jumps in entropy and temperature. Finally, there is the third characteristic wave, which is associated with the advection velocity, and this wave is linear. However, it's still discontinuous, and that's the wave associated with this contact discontinuity in the center, where the density jumps, but the velocity and pressure remain continuous. So the reason why this happens is because the characteristics are neither diverging or converging. The characteristics are propagating parallel to the wave. What this means is that the information from the initial discontinuity, where there was a jump in the density, propagates to the right with the speed of the advection velocity. So in hydrodynamics, we call these contact waves, but there are additional linear waves associated with pretty much any jump in material properties. As we mentioned in MHD, there is a more complex wave structure. So there's the central linear wave, but each non-linear acoustic wave splits into the two fast and slow waves, separated by a linear wave across which the electromagnetic fields can rotate. So this additional complexity in the wave structure is harder to resolve numerically because you're trying to pack more characteristic information into a smaller space. Now, I just want to mention, purely on the basis of the characteristic information, what's going to be the difficult parts to deal with numerically. So the rarefaction waves are typically not too bad because they are continuous. There can be issues when the characteristic speed changes sign across the wave. So if on the left edge of the wave, the characteristic speed is negative, and the right edge of the wave, the characteristic speed is positive, then algorithms that rely on the sign of the characteristic speed may struggle slightly there, and we occasionally need to add fixes. With shocks, what we need to be able to deal with is discontinuities. So the derivatives don't exist, and we need to be careful to make sure that we don't introduce any additional spikes, jumps, or oscillations. However, once we have an algorithm that can deal with that, the characteristic information will push everything in towards the shock. This means that shocks are typically very well resolved. So for algorithms that can deal with the sonic point where the characteristic changes sign and can also deal with discontinuities, it's often actually the contact discontinuities that are the hardest to get accurate. Because as soon as a numerical method introduces any smearing, that smearing will just be propagated along unchanged and hence keep smearing by the contact discontinuity, simply because the characteristic information always just keeps everything propagating parallel to it. Whereas in a shock, what we'll see is everything focusing in and staying sharp. Okay, so that was my recap and expansion of the material that we saw yesterday. So take an opportunity for a quick break to make certain that everything's focused and to have a drink. We'll be back in 30 seconds or so. And if you've got any questions, drop them into the chat. Okay, so I'm not seeing any questions at this stage, so we'll move on to the next part where we start looking at numerical implementations. And to do that, we firstly have to do a quick overview of how the numerical approximation works. So what we want to do is to solve a continuum partial differential equation on a computer. So the quantity that we're solving for, Q of X, needs, in principle, an infinite amount of information. That's because the continuum solution Q could, in principle, take totally different unpredictable values at every single point X, and there's an infinite number of points inside the real line. So this mathematical way of thinking is clearly useless when working with a computer with a finite amount of working memory. So instead, we're going to consider ways of approximating the solution, Q of X, in a way that uses only a finite amount of information. And there's three different methods that are used in the field. So the first method is the point value approximation used in finite differencing. So we're going to put down a grid of points. And in this case, in the figure here, I'm illustrating it in one dimension. I've labeled each of the grid points with an integer I, and I'm assuming there's a finite number of them. So at each grid point, what we're going to do is we're going to store the value of the solution at this point. So we're either going to say that we know this value because it's given by the initial data or we've previously computed it, or alternatively that we want to compute the value at that point. When we want to link the solution at different points, then we have a problem because the solution Q of X is not known anywhere except at the individual points themselves. So what we have to do is to assume or impose what the form of the solution is between each of these points. For example, we could assume that the solution is given by straight line interpolation between each of these points. As soon as we have made that assumption, we immediately know the values of, for example, the derivatives everywhere, because we can compute that from our assumed interpolating polynomial. The second approach that we might take is to split the domain into individual cells and within each cell to store the average value. So this is the finite volume approach. In this case, We have some information about the solution Q of x at every point in the space-time, the average value near the point. So if we pick a point x at random, then we find within which cell it falls, and we know the average value of the solution in a neighborhood of that point is given by the thing that we stored within the cell. However, the exact value of the solution is known nowhere. There is no point in space-time where we can state that the value of the solution. So, in order to get the value of the solution at any specific point in space-time, we have to impose or assume what the general behavior of the solution is. If we assumed that the solution was piecewise constant within the cell, then we would replace the picture where the solid lines are interpreted as the cell values with the interpretation that the solid lines are exactly the solution itself. But we could equally well impose that the solution is piecewise linear or a cubic spline. Anything that works as long as the interpolating function is within any individual cell consistent with the average value within that cell. So the distinction between the finite volume approach and the finite difference approach is the finite volume approach is implicitly smearing out the local behavior of the solution. Because the finite volume approach is not claiming to know anything about the value of the solution, only about its average across a domain, that means that it never says exactly where it is with relation to a discontinuity. So this smearing out behavior is exactly what we want when dealing with discontinuous solutions, because it doesn't try and tell us the precise value, which has no meaning at the discontinuity. It instead looks at its average value within a region, which does have meaning by a discontinuity. The final approach is linked to finite elements. It's still reminiscent in some ways of the finite volume approximation because it's splitting the domain into separate cells. But instead of storing the average values of the solution within a cell, instead it typically stores the moments of the solution with respect to some function basis. So for example, if we were to think of the function basis as being simple polynomials, we would store the coefficient of x to the power 0, the coefficient of x to the power 1, the coefficient of x squared, and so on and so forth, all expanded about the center of the cell typically. So typically the 0th moment is linked to the derivative. The 0th moment is linked to the cell average, the first moment to the derivative, the second to the curvature, and so on and so forth. So this is fundamental to the discontinuous Galerkin method that Harold Pfeiffer is going to talk about later. So far, this hasn't been used much for relativistic matter simulations, and I hope I'll have time to talk about this in a bit more detail tomorrow. Right, I'll just check the chat because somebody dropped a question in. Can you please explain why the contact discontinuity wave is generated? Right, so contact discontinuities are essentially linked with changes in material properties. So for example, if you took a neutron star, then we expect the neutron star to have a crust and a core, and we also expect there to be distinct regions inside the neutron star, transitions from core or inner core to outer core, transitions from superfluid regions one to the next. And these would be associated, for example, with phase transitions or with jumps in the number of leptons or a particular change in the lattice structure or something like that. You can think of it essentially like the transition from the Earth's core into the Earth's mantle. So while these may be smooth, if you look on a small enough scale, they're going to be discontinuous. Now, they're not associated with the transmission of forces or any work being done. What you're seeing is something that's perfectly stable, but the properties of the system changes from one side to the other. For example, properties of the equation of state will change from one side to the other. So then if you have a wave that hits this interface, then what it's going to do is going to push this interface along. And it's this material interface being pushed along that is essentially linked to contact discontinuity. Okay. So having described the various grids that we might see in a numerical simulation, I'm going to focus on the short term on the finite volume approach, where we're storing the integral average of the solution across a cell. And what we do is we take our original conservation law, dq dt plus divergence of f is equal to 0. And then we're going to integrate that conservation law over a domain. So when we integrate over a domain, either over an individual cell within a domain or over the domain as a whole, what we're going to get by doing a spatial integral over that entire region, well, the integral is going to commute with the time derivative, leading us to have the cell integral average q hat I multiplied by the size of the volume for the first term, and then we can use Gauss's theorem or Stokes' theorem, or however else you want to think of it, to integrate the total divergence over the volume and replace it with the surface integral. So surface integral of the flux. So our equation of motion, our partial differential equation, becomes an ordinary differential equation because the time derivative of the integral average is given by the surface integral of the flux through the boundary of the domain. So this is the weak form of the conservation law, or it's one of the ways that we can write the weak form down. What we've done is we've used the integration approach to remove spatial derivatives from the solution. As the solution is discontinuous, this form of the equation makes perfect sense, even when shocks appear. So the mathematics of this are going to work out fine. So we can see from this equation that we're still not quite at a point where we can solve the ODE. Because in order to solve the ODE, we need to be able to evaluate the surface integral of the flux. Being able to evaluate the surface integral means knowing what the solution is at the boundary of the domain. But we don't know the solution at the boundary of the domain. We only know the integral average within the domain. So this brings us to the fundamental step in numerical methods for conservation laws. It is, how do we compute or approximate this boundary flux? Once we've got that, then we can immediately integrate forward to find what our cell integral average is. And we can solve the ODE using pretty much any standard methods, although I'll come back to in tomorrow's lecture some issues linked to that. So to be concrete, let's restrict to one dimension, which is what the figure on the right-hand side is doing. So we've got our general solution, which is a smooth sort of cosine-like behavior with a jump within the ith cell. We're going to represent this by the integral average by integrating over each cell. So if we make the assumption, do I want to do that yet? Sorry. What I want to do is to update these cell integral averages as represented by the straight lines by computing the surface integrals of the flux through the boundaries of these cells. Because we've restricted to one spatial dimension in this case, the surface integral is replaced by evaluating the fluxes at 2 points, 1 point to the right and 1 point to the left. Because of the way that the normals to the boundaries work, what we're left with is the interpretation that the cell integral average is updated by the flux out. Let me do it as the flux into the cell through the left boundary, so that's Fi minus a half, and the flux out of the cell through the right boundary, that's Fi plus a half. Of course, here into and out of are conventional language that are used on the assumption that the material is propagating from left to right. If the fluxes were negative, it would be corresponding to material propagating in the other direction. So the key point that we want to make from this formula, which is, whilst it looks like a discrete formula, is still essentially a continuum formula until we have a way of evaluating these intercell fluxes. The key point that we want to make is that it satisfies a discrete conservation property. And what I mean by that is expanded on in the exercises, but essentially the idea is the total amount of stuff inside the domain, the total amount of energy or momentum, is given by the integral of that stuff, the integral of Q over the entire domain. Because we're storing the integral average within each cell, the total integral over the entire domain is given by the sum of all of those cell integral averages, by the sum of the Q hats. Now, when we update from one time step to the next, we're updating it by using the intercell fluxes. And any individual intercell flux is going to appear precisely twice. So Fi minus a half appears with a positive sign when it's used to update cell Xi, but it also appears with a negative sign when it appears to update cell Xi minus 1. So that means all of the interior fluxes are going to cancel out. So that means that the update of the total amount of stuff is determined only by the fluxes through the boundaries of the whole domain. Inside the cell, all of these flux contributions cancel out. We have discrete total conservation. As we saw in the first lecture, having conservation is essential to ensuring that the Rankine-Hugoniot conditions are satisfied. So by imposing discrete conservation, we're going to ensure that the discrete Rankine-Hugoniot conditions are satisfied, and this will mean that any shock propagates at the correct speed. So we have a mathematical formalism using the weak form that is going to ensure that shocks make sense and discontinuities make sense. We've got discrete conservation that ensures the discrete Rankine-Hugoniot conditions hold, which means that shocks will propagate at the correct speed. So the shock is going to make sense, it's going to propagate at the right speed. We're 2/3 of the way towards an algorithm that is going to work for us. So let's look at the first algorithm that we have for computing the intercell flux. This is called Godunov's method, and it and its variants are the fundamental underlying method that is used in the finite volume approach. In essence, what Godunov is doing is it's making the assumption that the solution is piecewise constant within the cell. So as we said, the finite volume approach, you store the integral average. In order to evaluate the solution at any one point, we have to make an assumption as to how the solution behaves. So here the assumption is made that Q of X is given by the cell integral average Q hat. Now, at this point, we still can't compute the intercell flux. The reason is, in order to compute the intercell flux, we need to be able to evaluate F as a function of Q at the cell interface. So we need to know Q at the cell interface. And while we know Q everywhere, at an interface, we now have two values for the solution, one from the left-hand limit and one from the right-hand limit. So we have to impose or compute what the appropriate solution for future time is for that cell interface. And the way we do that is by appealing to the characteristics. So when the characteristic speed is positive, as in this picture at the top here, in that case, the characteristic speed being positive means that the solution is propagating from left to right. So while at the initial time there are two values for the solution cell interface, at all times immediately after t equals 0, it's only the solution to the left that matters. So therefore, we know that Q at the cell interface is going to be equivalent to whatever the value of the solution was to the left of the interface, which by our assumption that the solution is piecewise constant is given by the cell integral average for cell I. If it were the case that the characteristic speed is negative at the cell interface, then we know the information is propagating to the left, and so the solution we want to take is from the right of the interface. So we're going to use Q hat I plus 1. In general, the intercell flux is going to be some function of the cell averages or the solution on either side of the cell interface. The problem comes when the characteristic information changes across the cell interface. So we're working out what the characteristic speed is based on the data. We remember that it's perfectly possible, well, we expect the characteristic speed to depend on the data. If the data on both sides of the interface lead to characteristic speeds that change across the interface, then it's harder to compute exactly what the correct solution is. In this nonlinear case, we're going to have to solve that Riemann problem, and we're usually going to have to do that approximately. However, for simple cases, what we have here is an algorithm that will work in steps. We are imposing that the solution is piecewise constant. We're then using the characteristic information in order to take either the left or right state as the appropriate solution at the cell interface. And then we're computing the intercell flux from f of whatever that value q is. From the intercell flux, we've got, if we go back up, from the intercell flux, we've got the right-hand side of the ordinary differential equation. We can evolve that forward in time in order to get our new cell averages. Right, so when the characteristic information is ambiguous, or when we're working with the nonlinear system, where we've got multiple pieces of characteristic information, it's most straightforward in order to approximate the solution to the Riemann problem in order to solve for the cell flux. And the simplest approximation that has useful outcomes is linked to the names Harten, Lax, Van Leer, and Einfeld, abbreviated to HLLE. So what this is going to do is it's going to find the intercell flux based on the values to the left and right of that interface, QL and QR. And in Godunov's method, those are the cell integral averages. Now, the way that HLLE works is it's based on characteristic information again, but in this case, we're not computing the characteristic information, we're imposing the structure of the characteristic information. So the assumption that we make is that there are two characteristic speeds and only two. So for large systems, this is obviously throwing away a lot of physics. We need to impose that psi minus is smaller than all characteristic speeds in the problem, and psi plus is larger than all characteristic speeds. So in the diagram in the top right, the imposed psi plus and psi minus are the only jumps that we're going to consider. We then impose that the solution jumps discontinuously across these waves and impose the conservation law. That is, we integrate over a small volume in space and time. Once we've imposed conservation, then we can compute in closed form the appropriate state solution in between these waves. And we call that Q star, the intermediate state. Then we can get the flux as appropriate. So if both psi minus and psi plus are positive, then the intercell state is going to be given by Q left. If both psi minus and psi plus are negative, the intercell state is given by Q right. If they switch sign, which is the interesting case, then the intercell state is given by Q star, which is this simple algebraic closed form solution in terms of the speeds in Q left and Q right. And then we get the intercell flux from F applied to the intercell state. So the HLLE method has some very nice properties. It's cheap to compute in comparison to the exact solution for any sizable system. So for relativistic hydrodynamics, using HLLE can be between hundreds and thousands of times faster than the full exact solution to the Riemann problem. It's fairly cheap to compute in part because we tend to use simple approximations for the characteristic speeds. Particularly for relativistic problems, you can use that the minimum and maximum characteristic speeds are given by the speed of light, although that is a bit less accurate than if you have a better approximation. HLLE is not specific to one model, so you can lift it and apply it to MHD or relativistic elasticity or more complicated systems with no change. And finally, it's linked to positivity preservation. So quantities like density, they should remain positive at all times. And when tied to an appropriate update scheme, HLLE ensures that positivity of density and energy is preserved. Unfortunately, HLLE has some major problems associated with it. In particular, because it does the calculation based on the outermost waves, which are pretty much routinely the nonlinear waves, the information about linear waves, like contact discontinuities, is thrown away when making the HLLE approximation. This means that HLLE tends to introduce a smearing across any linear wave. And as we discussed from the characteristic viewpoint, once that smearing is induced, it doesn't improve. It tends to get very bad. So for hydrodynamic problems, it's often the case that whilst HLLE isn't brilliant on contact waves, it's not too much of a problem. But for MHD, there's more linear waves. They're closer to the nonlinear waves. And so HLLE is often too inaccurate to be useful. So more complex approximations will either work to ensure better behavior when the waves aren't discontinuities, or it will work to ensure better capturing of the linear waves. And it's often necessary for MHD. But the steps that we're going through, so imposing the form of the solution and then approximating the intercell flux, are going to be consistent from one to the next. Okay, so that is the first outline of Godunov's method, our fundamental tool that everything else will build on. We're going to go into rather more detail in the next slot, so drop any questions that you may have about where we've got to now, so that we're ready for more detail when in the next half hour or so. Okay, so I'll just wait another 30 seconds in case there's any questions people want to. There we go, first one. Godunov schemes essentially applies to finite volumes, right? Now, here's where we need to be a little bit careful. I would always associate Godunov schemes with finite volume methods because that's the place where they're usually explained. However, for low order methods, as we'll get onto later, it's pretty much always the case that you can reframe any finite volume method as a finite difference method. And these reinterpretations of methods in different contexts can be incredibly useful. I'm about to reinterpret Godunov's method in a different way right now. So yes, I personally would always think of Godunov's method as being associated with a finite volume approach, but you can reframe Godunov's method in terms of finite differences. You can think of it as an extension of the upwind method, which is a standard finite difference method using an adaptive stencil in some sense. It wouldn't be the way that I would think about it, but there certainly are other members of the community that will be perfectly happy with that way of thinking. Right. So as I just mentioned, we are going to have to reinterpret the schemes. Oh, another question come up. So which one of the finite volume and finite element methods is more effective and why? The answer to that is incredibly lengthy, and I hope I will get to it in the next lecture. So I would say briefly today, if you're dealing with solutions that are differentiable, then you would always want to work with spectral or finite element methods because they're more efficient and they're reasonably straightforward in those cases. If you're working with solutions that are discontinuous, like matter simulations, and you're doing it today in our field, then finite volume is the way to go if you need a result as soon as possible. However, there is a lot of effort, particularly in the Newtonian CFD community, going into making finite elements work. And so it may well be possible that finite elements is the most effective solution in the future. But right now, I think there's a lot of problems to overcome. And I'll talk about that more tomorrow, I hope. So how's the derivative of f is related to the compact objects physically? Well, one way that you can think about this is in terms of a force argument. So if we're thinking about a neutron star as being a stable or static solution, it's got each individual fluid element essentially has two forces on it. You've got the force due to gravity, which is trying to pull that fluid element towards the center of mass of the object. And then you've got the force due to the other fluid elements that neighbor onto it that are trying to push that fluid element away. It doesn't want to, the atoms or particles within that fluid element going into its own fluid element. So that's essentially the pressure gradient. So the derivative of the flux is the pressure gradient. Now, once the fluid starts moving, then you have to interpret that in an appropriate frame. So in essence, the derivative of the flux is giving you what's the force on the fluid element in the lab frame rather than in the frame of the fluid element itself. Okay, next question. Do we also construct initial data in a way suitable for finite elements and finite volumes accordingly? And can you explain how? It's clear to me in the case of finite differences, but do we simply average the initial data or something? Right. At the moment, the standard approach is to exploit the fact that finite difference and finite volume schemes are the same to second order. So you evaluate at the center of the cells and you pretend that the point value is the integral average. And that's for smooth solutions, and at least for continuous solutions, and all our initial data is going to be continuous, that is sufficiently accurate to be going on with. For finite elements, things are more difficult, and in that case, you've got a few options, and I'm not entirely certain what the standard approach is. What I would tend to do is to rewrite the initial data solver to make it explicitly compatible with the finite element approach. But yes, that is a non-trivial problem. Okay, so moving on. So the problem with Godunov is that it just isn't good enough for practical simulations. It will work. We could write a code using Godunov's method, compute the intercell flux using an approximate Riemann solver, and we could extend this to 2 or 3 dimensions by solving a Riemann problem for each intercell flux through each cell face. But the problem is that the algorithm isn't very accurate. So we can see this from the images on the right-hand side. So this is an image I've taken from the exercises, and I haven't zoomed in quite the right place. Let me zoom in there. Still not right. Anyway, so in this case, I've solved the advection equation, a simple linear equation, using smooth initial data given by the black line, and I've advected it once around the periodic domain. And we can see that the peak values have been clipped by roughly 10% in one cycle. We can see that the peak is slightly offset, so the phase accuracy isn't brilliant. So both the magnitude and the phase are inaccurate already after one period. More importantly, we look at how the error goes, and we're measuring the error in an appropriate norm over the domain. And we look at how that is scaling with the grid spacing delta x. And what we find is that that error norm is reducing proportional to delta x. So if we wanted to reduce our error by a factor of 10, we would have to reduce the grid spacing by a factor of 10. Now, the computational cost does not go down by a similar factor of 10, because as we change the grid cell size, what's going to happen is the grid cell size has to change in each of the 3 spatial dimensions. And in addition to that, the time step restriction means that the time step also has to reduce by that same factor. So in order to get the error to go down by a factor of 10, we have to increase the computational cost by a factor of 10,000. Now, because gravitational waves need high phase accuracy in order to make certain we get the frequency correct, we need to get much higher accuracy than we'll see using Godunov's method at these type of resolutions. So we could throw computing power at the problem. But we would typically say that in order to efficiently use the computing power available to us, we want an algorithm that's higher order accurate. Ideally, we want something that was 4th order accurate or better. That is, the error would scale as delta x to the 4. The reason for that is because then if we increase the computing power available to us by a factor of 10, the error would go down by a factor of 10, rather than a factor of 10 to the 4th power. So we want to use higher order methods. We want to work with higher order methods. But the problem is that tends to cause us problems, and those problems are linked to the shocks. So the way that we're going to think about this is to we are going to sorry, it's giving me something strange. Right, let's ignore that. So we're going to rethink the Godunov method as introduced before. And we're going to now think of it in terms of a three-step process as illustrated by the figure on the right. So the first step in the Godunov method is to start from our cell average solution and then impose what the structure of the solution is, that within each cell the solution is constant. So this is the integral averages we've reconstructed to an assumed form of the solution everywhere. We then compute the intercell fluxes, and locally this approximately advects our solution at a certain speed. So we now have a roughly piecewise constant solution that isn't aligned with the cell boundaries. So this is the different way of thinking about the solution. Rather than just thinking about the flux at the cell boundaries, we're now thinking about the evolution step as moving along the entire solution. Now this is somewhat approximate. As we know, the characteristic speed varies with space, so the resulting solution that we get is not going to be exactly piecewise constant, as the matter piles up in some areas and spreads out in others. But as a sketch, this is roughly the sort of thing that we're doing. We could do it exactly if we wanted to. So we now have an exact form of the solution. We've gone from a piecewise constant solution aligned with the cell boundaries to a solution that isn't quite piecewise constant and definitely isn't aligned with the cell boundaries. So this is an evolve step. We've gone from Q of x at the initial time to Q of x at a later time. And finally, to complete our one integration step, we want to average over each of our cells as before. This gets us back to the cell integral averages. And this final step means that we've ended up with a solution that we can think of as being roughly piecewise constant as before. So now we want to think about how accurate each of these steps are. So going from the end, the averaging step takes a given solution and performs an integral on it. That's something that we can do in principle exactly. The evolution step takes a given solution and evolves it forward in time by solving an ordinary differential equation. Now it needs the intercell flux, which we usually approximate, but in principle we could solve that exactly, and we could solve ordinary differential equations to essentially arbitrary high accuracy. The reconstruction step at the top, that's the point where we've introduced our approximation. By imposing that the solution is piecewise constant, we have simplified our problem and lost accuracy at that stage. So in order to increase accuracy, to go to higher order methods, we need to move away from doing piecewise constant reconstruction. Instead, we want to think about, for example, replacing a piecewise constant approximation within the cell with a piecewise linear reconstruction, assuming the solution is a straight line. And then we might move up to quadratic functions and higher order. And this would give us higher accuracy. Unfortunately, it also introduces other problems. So the problems that we see are essentially ones that you would expect if you've done a signal processing course and have seen Gibbs oscillations in the past. So what I'm going to do here is talk about reconstructing a discontinuous function. This is what we're doing within cells. What we're trying to look at is how the solution behaves across intercell boundaries. So the classic description of Gibbs oscillations is where you do a Fourier series representation of a discontinuous function. So in this case, we've got a partial sine series. If we take the first 10 terms in the Fourier series, we end up with this blue dashed line that oscillates either side of the interface. And those oscillations are problematic. So there's three standard ways that we could think of trying to get rid of those oscillations. First, we could decrease the size of the grid cell, but there's no scale here, so that has absolutely no impact other than squeezing the oscillations closer to the discontinuity. So the second thing we could do is to try increasing the number of terms in the Fourier series sum. And if we do that, it has exactly the same impact. It doesn't change the amplitude of the oscillations, it just pushes them ever closer towards the discontinuity. So the final thing that we might say is, well, we don't want to use Fourier series, that's a mixture of sines and cosines. We might instead want to use simple polynomials, or maybe Legendre polynomials, or Chebyshev, or any other function basis expansion. And unfortunately, that doesn't make any difference either. These oscillations are there in all cases. So the emphasis here is that these Gibbs oscillations will destroy our numerical accuracy. If your scheme introduces Gibbs oscillations, then they will typically blow up in a few oscillations, in a few iterations, destroying the accuracy of the scheme. And typically when dealing with a hydrodynamic simulation, they lead to negative pressures, negative densities, which when combined with standard equations of state cause the simulation to crash with unphysical numbers. So what we really want is our solution to be monotone. That is to say that the scheme doesn't introduce oscillations. So in particular, it doesn't introduce any value that is smaller than the minimum at the start or larger than the maximum at the start. And the depressing point is Godunov's theorem, the same Godunov as in the Godunov scheme. He proved that if you want your scheme to be monotonic and your scheme is linear in the sense that it doesn't care what the values of the data are in how it does its differencing, then the only way the scheme can be monotone is if it's first order accurate. In other words, something like Godunov's method is as good as you can do. Now, we have one loophole left by Godunov's theorem, and it's this word linear. That says that we're going to do the same thing at all points in space, the same form of the solution, independent of the data. Whilst the values themselves will depend on the data, the form will not. So the entire past 50 and more years of computational fluid dynamics has focused on creating non-linear schemes for locally modifying the algorithm based on the values and form of the solutions. And this is solely to avoid Gibbs oscillations. It's this non-linearity, both in terms of the reconstruction step and also in terms of the solution for the intercell fluxes, that makes matter models so much more computationally expensive than methods for smooth solutions like the spacetime. Right, so here is our first nonlinear scheme, which is using a piecewise linear approximation. So in this scheme, what we want to do is to impose the form of the solution is going to be a linear function within the cell. And the linear function is going to have slope sigma or sigma bar. So therefore, the form of the solution is going to be a straight line centered on the integral average value. Now, we can easily think of different ways of approximating the slope based on the cell integral average and its neighbors. And the forward, backwards, and central differencing algorithms suggest the upwind, downwind, and centered slopes. But we can see from the top right-hand figures that all of these separate slopes are going to give us oscillations individually. So for example, the downwind slope gives us big jumps in this central cell xi. The centered slope gives us big jumps everywhere, and the upwind gives us big jumps in this cell xi minus 1. So what we want to do is to choose the slope appropriately so that we get the highest accuracy that we can whilst trying to avoid the jumps that might give us oscillations. And the way that we do this is to try and check the data itself to see when there may be problems with shocks. The easiest thing to do is to say that, well, if the upwind and downwind slopes give different signs, then we're near some extrema, we're near some shock. And at that point, we would reduce our method to Godunov's method. We would reduce our slope to 0 so that the approximation is piecewise constant there. Now, the min-mod slope limiter, which is what I'm showing below, is a simple but not particularly accurate slope limiter. And that works by picking the slope that is smallest in absolute value. So we can see from the picture that we've now got a set of slopes that are all fairly small, and there's no oscillations being introduced. So if we combine min-mod reconstruction with the computation of the intercell flux through, for example, HLLE, and a higher order ordinary differential equation solver, then we can solve any of our equations to better than first order. Unfortunately, min-mod is not much better than first order. The exercises will show you examples of this, and while you will see for high enough resolution that the convergence is better, than the accuracy is better than Godunov, it's not hugely better. So instead, we're going to need to look towards both more absolute accuracy, which can be done via slope limiting, or alternatively, higher order methods in general. So I'm going to take a diversion away from finite volume methods, and the reason for that is explained in a sketch in the figure on the right-hand side of this picture. So while I'm talking about finite differences, the first thing I want to mention is the problems with the finite volume approach in higher dimensions. So the formula that I've written here is our one-dimensional update scheme. We're computing the update via the intercell flux. Now, this is only accurate in one dimension because we remember that the intercell flux really comes from a surface integral over the boundaries of our cell. In one dimension, that surface integral is exactly given by evaluating the fluxes at these points. However, if our function varies in high dimensions, then in the higher dimensions, the intercell faces become one or two dimensional. The solution is going to vary over those faces. So therefore the flux is going to vary over those faces. So the surface integral over those faces needs to be approximated. Now the most efficient way of approximating an integral in general is to use Gauss quadrature. So where in Gauss quadrature you evaluate the integrand at k points in the boundary, and that gives you 2kth order accuracy if you choose the points and the weights appropriately. So in higher dimensions, the reason that Godunov methods and slope limited methods work is because if you evaluate in the center of the faces, as I'm doing here, then that's equivalent to Gauss quadrature using the midpoint rule. So that's second order accurate. However, you can't get higher than second order accuracy by just evaluating at the center of the faces. If you evaluate it at 2 points in each face in 2 dimensions, then that's going to correspond to fourth order accuracy. But in 3 dimensions, we'd have to evaluate at 2 points per dimension per face. So that means we'd need to reconstruct the solution to 4 points in each face, solve 4 separate Riemann problems. As the order increases, the computational cost and the computational complexity in particular goes up very rapidly. So for this reason, high-order finite volume methods are rare in the field, although there are a couple. Most people working with finite volume methods concentrate on absolute accuracy, particularly around shocks and contacts, and get second-order convergence. To get higher order convergence, the standard approach we use is to work with finite differences. So, this may appear that I'm rewriting the standard update formula, but I want to emphasize that now that I'm working with finite differences, this is not the same update formula as before, because I'm updating Q, the point value of the solution at the grid point I. This is not Q hat, the integral average of the solution over the cell I. That also means that we should change our interpretation of the term on the right-hand side. So before, in the finite volume approximation, the F's were the intercell fluxes. In the finite difference approximation, there are no cells, so there can't be intercell fluxes. Instead, we're interpreting F as being some function that, when written in this differencing form, Fi minus a half minus Fi plus a half, approximates the derivative of the flux to an appropriate order. Now, what does this mean as a practical computation? It means that we calculate the flux not at interfaces, but at grid points. We calculate F at the point xi. We then reconstruct the fluxes to the half points. So we reconstruct the fluxes from f of I plus 1, and so on and so forth, to f of I minus a half. And we then have the flux differencing formula like this. Because this method is constructed so that the difference between the flux terms approximates the derivative, these one-dimensional single evaluations are going to extend cleanly to higher dimensions without having to integrate over the cells in the same way as you would for higher order methods. At the same time, because we've written the update term in terms of the half-valued fluxes, and that's used for both of the neighboring points, we still have the flux telescoping property. We still have total discrete conservation, and so the Rankine-Hugoniot conditions will be correct. So this would appear to be wonderful, much better. By directly dealing with the flux and not going through the solution, we're bypassing all the issues with intercell fluxes and with Riemann problems and so on and so forth. Unfortunately, there was a lot of physical information contained or approximated in the reconstruction intercell flux and Riemann problem approach that we've thrown away. In particular, there's information about the characteristics, the characteristic directions. So that means a naive finite differencing form is horribly unstable because it doesn't take into account which direction information is propagating in. So we would introduce Gibbs-like oscillations that rapidly kill the simulation if we just did something straightforward. So we need to build that characteristic information in to our method somehow. And the standard way of doing that is to use a flux splitting. So we're still going to work with the fluxes, but I'm going to split it into two parts. One part that propagates in the positive direction, F plus, and one part that propagates in the negative direction. Now, it's a bit strange to talk about the flux propagating when it's really the solution propagating. But what we mean is that the derivative of each part with respect to Q has to have a specific sign. So df plus by dq has to be strictly positive. df minus by dq has to be strictly negative. And an example of how you construct that is given by this Lax-Friedrichs flux on the right-hand side. So that's similar in spirit to the HLLE approach to solving Riemann problems. Having reconstructed both the positive and negative fluxes, so we reconstruct the positive fluxes from left to right and the negative fluxes from right to left, so it's appropriately upwinded for the direction, we can then add together these two reconstructed fluxes to get F itself from F plus F minus, giving us the half integer terms which we can use to update the finite volume approach. So this sort of finite differencing approach is used by codes like David Rodriguez's Whiskey THC method in order to get the current most accurate simulations. Okay, so we have one final topic to cover. I want to briefly summarize what extensions we're going to need for MHD, but we've only got about 10 minutes left. So if you've got any questions at this point, you can drop them in the chat or you can leave them towards the end. But in the meantime, we'll have another 1 minute's break or so. Right, as we've only got a short amount of material left to go, I will push on and answer any questions left right at the end. So I want to talk about the additional steps that we need in order to evolve once we add magnetic fields to the problem. So the equations of motion we discussed in the previous lecture. For the Euler equations for hydrodynamics, we're going to be evolving 5 equations of motion, the 4 associated with energy and momentum conservation and the 1 associated with the continuity equation. To include MHD, we have to add in 3 additional equations of motion for the magnetic field. But those equations of motion come with additional constraints, some of which, for example, allow us to compute the electric field, and some of which constrain the behavior of the magnetic field itself. Now, everything I have discussed so far and all the extensions carries directly over to calculating the update terms for MHD. That's because MHD is written in flux conservative form. So every single technique will work forward. The problem that we have is that one of the constraints specifically, the no monopole constraint that the divergence of B has to vanish, causes significant problems. Now, constraint equations are a fact of life in numerical relativity. In the 3+1 decomposition, we see the Hamiltonian and momentum constraints that are usually not enforced. They're usually used as an independent measure of the accuracy of the simulation. However, it's been known for decades. This is the classic paper by Brackbill and Barnes from 1980 that showed that if you don't correct for the fact that the divergence of B should be 0, then your simulation will fail in tens to hundreds of steps. Now, there's essentially 2 types of approach for forcing the constraint to be 0 or avoiding the problems with the constraint. So the first one is to introduce the constraint div B essentially as an independent variable, and then to add multiples of this constraint to the equations of motion. This is the constraint damping approach, where we add the form of the constraints to the equation of motion in such a way that when we write or compute the equation of motion for the constraint itself, which is of course going to be implicit in the equations of motion because the constraint is an operator of terms that appear in the equations of motion. Once we write this equation of motion for the constraint, we want it to have the form that the time derivative of it is proportional to the constraint itself, with a proportionality constant which is going to be negative. If this happens, then the solution for the constraint is that it decays exponentially fast with some e-folding time. And in nearly all cases, because we're adding this constraint by hand, this alpha term is going to be a parameter that we can choose by hand. Now, to avoid feedback at specific points, it's typical to also add additional terms so that the constraint is propagated as well as damped. The main advantage of the constraint propagation is its simplicity. When we've got a framework for solving large systems of PDEs, as we've built for solving the rest of the equations of motion, then adding one or two equations of motion for the constraints and similar terms, and a couple of extra source terms, that's very straightforward to add to the effective ODEs that we have. So when doing the first attempt at solving any system with constraints, I would always reach for constraint damping as a simple approach. However, the disadvantages of constraint damping can be substantial. You've got to hand tune the parameter which is associated with the damping type. You need to do that sufficiently quickly so that the constraint remains at a sufficiently low level, but not too quickly, because if you try and overdamp the system, you make the numerics unstable. The mathematical status of constraint damping is somewhat dubious. There's some results suggesting that the modified system isn't properly well posed. The interaction of the violations with grid boundaries, particularly adaptive mesh refinement grid boundaries, can be very messy. You can find that in some simulations that use constraint damping, the imprint of the grid boundaries can be seen both in the variable controlling the constraint propagation, but it can also feed back into the physical terms themselves, which is very much not what we want. And finally, from a philosophical point of view, it's very much not clear what level of constraint violation is acceptable. I mean, as soon as the constraint is anything other than 0, we have a solution that doesn't correspond to MHD. So what exactly does it correspond to? So the alternative approach is instead to enforce the constraint vanishes at the discrete level, so that when we convert from our covariant divergence to a discrete divergence, we have divergence of B vanishing. And the standard way that this is done at the moment is to use the vector potential. So we remember that the EM fields are described by the Faraday tensor, and the Faraday tensor can be written as the antisymmetric covariant derivative of the vector potential A. So we're expressing, for example, the magnetic field as the curl of A. This means that if we write things explicitly in terms of the vector potential and then compute B from it as a curl, because the derivative of the curl automatically vanishes, that's automatically going to preserve the constraint. Now, this introduces some conceptual issues, both at the continuum level and also at the discrete. So at the continuum level, the vector potential is not unique. You can add the gradient of any scalar field to the vector potential and return the same magnetic and electric fields. So this means that there's gauge freedom in the choices of how you evolve the vector potential. And currently the preference is for something like the Lorentz gauge, where you're evolving the vector and scalar potentials, essentially driven by the electric field. You might think that an algebraic electromagnetic gauge would be preferable, but results from probably about 10 years ago out of the Illinois group showed very clearly that what we want to do is to propagate the vector potential to avoid any problems being introduced at grid boundaries. The discrete issue is that the grid structure is now going to be conceptually more complex. So this figure I've lifted from the recent paper from Bruno Giacomazzo's group describing their recent Spritz code, showing where we should think within a single grid cell the different quantities live. and we can see that the vector potential is living on grid edges. That means that we can compute via the curl the magnetic field at the cell centers in order to reconstruct the magnetic and electric fields at cell faces in order to do the appropriate updates. So our algorithm will have to become more complicated. Right. So in summary, my personal approach to dealing with numerical methods for relativistic fluids is to focus conceptually on the finite volume schemes and to think about characteristics, to think about discrete flux conservation, and to focus on the reconstruction methods for improving accuracy. However, whilst that is useful for conceptual understanding, I think it is essential for getting high order accuracy, which we're going to need to get the necessary accuracy for our simulations, that we extend that intuition and apply it to other methods, finite difference approaches, and maybe on towards the finite elements and DG methods. When we move to the more complex physics, we have to be able to deal with the constraints, particularly in MHD, the divergence B constraint, and that's introducing new conceptual complexities. So the near future aspects for the numerical methods are almost certainly going to be around higher order accuracy, and in addition, combining that with constraint enforcement and possibly moving to non-conservative systems. So we'll talk about extensions both in terms of the physics and in terms of the numerics in tomorrow's lecture. Right, thank you very much for your attention. Any final questions? Chip in the chat or... Okay, so how is the discrete time interval required for the simulation chosen? How to balance the accuracy of the simulation and the total computation time by choosing the proper time interval? Right. So the fundamental limit that we have from the flux terms, from the information propagating back and forth, is called the Courant-Friedrichs-Levy limit, the CFL limit. And in the first lecture, I talked about it in terms of the past domain of dependence. But in terms of numerical methods, it's usually instead discussed in terms of the characteristic speeds. So what you need is that your numerical scheme, when it's predicting the value of a future grid point or grid cell, considers values from all of the grid cells whose characteristic information may travel to this cell. So what that essentially means is that in order to remain stable, the time step must be approximately less than the grid cell size divided by the maximum characteristic velocity. And because that maximum characteristic velocity is usually slightly less than the speed of light, the delta t is going to be essentially delta x by c. Now, because we're evolving the matter on top of the space-time, and the space-time does have information propagating at the speed of light, the delta t, the discrete time interval, is usually going to be determined by the space-time evolution. The matter evolution is always slower than the space-time evolution, and so we have to let the space-time set the time scale. So that means balancing the accuracy of the simulation, the total time, by choosing the proper time interval. For the matter, we don't have a choice. We're fixed by what's going on with the space-time. Now, having said that, there are workarounds in certain cases. For example, if we're dealing with something that's slowly evolving, or if we're dealing with a weakly coupled system, then it's possible to evolve the space-time and the matter using different time steps. examples of this would be Harold Dimmelmeyer's work about 10, 15 years ago on simulations of core collapse supernovae. He was using a very different method for updating the space-time, but he explicitly had different time steps for space-time and for matter. So these sort of variable rate calculations or variable rate time integrators can be used. I have seen some experiments in using them for neutron star type simulations. And in those cases, you're setting the time step for the hydro from delta x divided by the maximum characteristic speed. The maximum characteristic speed is associated with the acoustic waves. So it's usually going to be roughly around half to 2/3 of the speed of light. So you don't gain a huge benefit. For that reason, I haven't seen much general work done on variable rate integrators. So unfortunately here we're limited by the time step for the space-time.
Okay, I don't see any question. Are there any last questions? Yeah. Someone wanted to ask some question about the Einstein toolkit. This would be a good time to ask that also.
Hi, this is Swarnim. I wanted to ask you some questions. So I'm currently using this RNS code initial data and evolving it with GR Hydro.
Yes.
So I'm trying to use this V05 reconstructor.
Right.
So, but I'm facing trouble with the atmospheric control. So what's happening that after around 20 time steps, I'm looking at the maximum density and the maximum pressure, they come down to the atmosphere level, and I start getting NANs. So while setting up what I did, I used the atmosphere to be around 10 to the power minus 10, and then I set the tolerance quite high to so 1000 times, so that is 10 to the power minus 7. So by that I'm able to run the evolution, but what's happening is I'm also perturbing the star, so the perturbations are damped, and the total the density is also decreasing. So I'm guessing that this is happening because of the high tolerance level, that near the surface the values are converted into atmosphere. So can you suggest something to get over this problem?
So the implementation of the V05 method within the Einstein toolkit, I have to admit I haven't looked at that particular implementation in quite some time. So what I'm going to say is largely based on when I was working with that implementation probably around 10 years ago. So that implementation is highly problematic for reasons that I've been hinting at through this talk, and is also hinted at through the exercises here. So when you do high order reconstruction, such as a Wiener scheme, it's, in order to be stable near shocks, typically needs to do the conversion to the characteristic variables. So when it does that conversion, you're taking the fluxes and the variables, and you are multiplying by the matrices of the left and right eigenvectors. Now, the problem is that the accuracy of that transformation from conserved variables to characteristic variables and back is limited by the accuracy with which you can compute those matrices. And that in itself is essentially linked to the condition number of those matrices. And unfortunately, the condition number for the eigenvalues and eigenvectors, that Jacobian matrix, is essentially proportional to the inverse of the density. So as you go towards low density, the condition number blows up. The accuracy with which you can do that conversion drops away, and the accuracy of the Wiener scheme falls apart. Unfortunately, if you move towards doing the reconstruction on the standard variables rather than on the characteristic variables, then it doesn't tend to behave well near discontinuities. So to get around this, you need to be rather more careful in what's going on in the low density regions. I would suggest looking at the Wiener implementation within David Radice's Whiskey THC code, which you can download from his website. That's a different implementation of the Wiener code itself. I think it's rather more reliable than the one that's used within the toolkit. Within the toolkit, I would definitely trust the implementations of the piecewise parabolic method, PPM. That is, as implemented in the toolkit, a finite volume method, so you're only going to get asymptotically second order accurate results, but the absolute accuracy for standard grid resolutions is going to be pretty good. So at least for moderate term evolutions, you're going to get accuracy that isn't much worse than a fifth order Wiener method. Obviously, if you could afford to go to a higher order Wiener method, then you would do better. The areas where a Wiener scheme would really excel is if you're having to do an evolution for long periods of time. If you're doing hundreds of milliseconds, many oscillations, then it's going to damp the results much less than PPM would. Okay, so I don't think it's anything that you're doing. I think it's the implementation of that particular algorithm within the toolkit. I'm not sure that I would trust it.
Yeah, I actually did some runs with PPM as well, and it's working properly. But I was trying to use Vino 5 because I wanted to see some higher order modes excited in the star. That's
yes. So the issue about higher order modes, so overtones, unfortunately, merely going to higher order numerical methods won't necessarily get you the higher order modes, because it's more likely that it's the time resolution of the length of the signal that you'll need in order to get that, rather than pure numerical accuracy. If you sort of look at what the length of your signal is and work out what your binning frequency is based on the time step, then you may well find that the limitation is not so much the numerical accuracy, but the accuracy of your FFT based on the density of your signal. So for that, you're more looking at using finer grids and integrating for longer time. Now, it may be that you still need the high accuracy methods in order to capture that information. Maybe it's damping the high order modes more. But my first thing to check would always be, what's the length of the signal, what's the binning frequency, to make sure that it's actually not the FFT part that's causing you the issue.
Okay. Thank you.
Okay. So in the chat, Mukesh has asked why I ignored the diffusive term. Now, there are multiple reasons for that. And given that I'm on this slide already, I would recommend that people take a look at this paper from a couple of years back by Mark Alford and Rizzola and Hanauska and the Frankfurt group. So not just this paper, there's a couple of other linked papers where they're looking at the importance of bulk and shear viscosity in neutron star mergers and when it's actually important. So there's a number of reasons for ignoring the diffusive terms. One is that the status of non-ideal hydrodynamics in relativity remains, in my mind, somewhat controversial. So unlike the equations of motion of ideal hydrodynamics, there's still questions around the causality of the models. There's no universally agreed set of equations of motion, and there's a whole zoo of additional terms that we would need to add, and it's not straightforward in an agreed way as to how we would do that. From a more physical point of view, there are estimates of the impact of the diffusive and dissipative terms that you would see during particularly the in-spiral phase, and essentially they are negligible. So there would be no impact whatsoever by on the observable signals on ignoring the diffusion and dissipation. Now, the Alford et al. Papers start estimating when these terms would have an impact based on particular reactions, based on particular dissipative interactions. And in particular, they say that if you were able to resolve motion and oscillations on scales of the order of 10 meters, then it might start having an impact. So at the point where our numerical simulations start getting down to grid cell sizes of around 10 meters, and maybe a bit below, that's the point where diffusion would start having a measurable impact on our simulations. At the moment, the highest resolution simulation that I know of is from about 4 years back by the Japanese group led by Kyuchi, where they evolved the post-merger remnant in full MHD with a grid cell size of 12.5 meters. So that's right on the edge of the point where diffusive terms start to become important. The majority of the simulations and the images that I'm showing, they've got grid resolutions around 100 meters or maybe higher. So at the moment, the numerical limitations mean we simply don't have enough resolution in order to, that the impact of the diffusive term would be important. However, having said all that, there is some work on adding dissipation and diffusion, and it is going to be important. We just don't know at what level. The Alford et al. Papers are one of the few papers that actually attempt to quantify this based on existing state-of-the-art simulations, but I would very definitely take their numbers more as indicative of the order of magnitude that is relevant rather than quantitatively precise.
Okay, any more last question? So if not, let's thank Ian once again for this great lecture. And I see you tomorrow, Ian, and the rest of you in the afternoon.
Thank you all. I'll see you tomorrow.
Thank you. Yeah, thank you very much. Bye all.
Bye.